Today we'll be looking at the topic electrolysis. Now I know electrolysis, when you listen to that word you think of electricity, right? So yes, it does have something to do with electricity. So before we actually go into the topic of electrolysis, we have to first understand what is electricity. If you look here, you'll see a circuit, right? So in this circuit we have a positive, this is our battery, right? Our battery cell. This is the positive end of the battery, and this is the negative end or the negative terminal of the battery. Now from the negative terminal you have electrons flowing through the circuit, right? Now once the electrons are able to flow freely through the circuit, it's going to cause this bulb here to light. All right, now just for you to remember, electrons flow from the negative terminal to the positive terminal. However, current flows from the positive to the negative. So try not to mix up your physics and your chemistry. Okay, right, so our electrons are flowing, and electrons are charged particles. So electricity is the flow of charge around the circuit, carrying energy from the power supply, which is here, around the circuit. Okay, now the energy can only flow if there is a complete circuit from the battery through the wires to components and back to the battery again. So let's say once our switch here is open, no electricity will flow because the electrons can't pass through this if it's open, right? But as soon as the switch closes, the bulb lights, right? So that means once we have a full closed circuit, we have electricity passing through. Now, substances can be divided into two main groups based on whether they are able to conduct electricity or not. So if they are able to allow the passage of electricity, we call them conductors. If they do not allow the passage of electricity, we call them non-conductors, or we also call them insulators. Let's look at an experiment to classify substances as conductors or non-conductors. So let's look at this first circuit. So we have our power source, we have our bulb, material to be tested, and the switch. When we close this switch, if this material to be tested is a conductor, it's going to allow the flow of current, right? If it is not a conductor, of course, there will be no current flowing. If current is flowing, the bulb will light. If no current is flowing, the bulb will not light. Similarly, in this electrical setup, we have, this is what we call an electrolytic cell. This is a circuit diagram for an electrolytic cell. This is how we draw it. So we draw our battery, followed by straight lines, which represent the wires. Our components here are the bulb, the switch, and our electrolytes. All right? Now, if our liquid that we are testing is a conductor, our electrons are going to pass through here, through the electrodes, right? These poles here, the electrodes, right? This solution will conduct the electricity, right? And the electrons will continue going this way, right? Now, if this liquid is a conductor, then the bulb will light. If the liquid is a non-conductor, this bulb will not light. Conductors include materials such as metals, graphite, and molten aqueous or ionic compounds. All right, so we know this already. Metals, all metals such as aluminum, magnesium, sodium, gold, silver, all metals on the periodic table are conductors of electricity. Graphite, as you know, is an allotrope of carbon. It has a sea of delocalized electrons, and these are able to conduct electricity. So you would find a lot of electrodes are made from graphite. Molten and aqueous compounds, ionic compounds, that is, these contain moving ions, and it's the moving ions that are able to conduct electricity. So there are more than one type of material that can conduct electricity. Therefore, we classify conduction into two main types. These are called metallic conduction and electrolytic conduction. Let's look at metallic conduction first. Okay, so we have our circuit set up here, and we have our material to be tested, which is our metal. Now this is expanded to show how you have your metallic bonding in your metal. All right, so we know that metal structures have the cations that are packed in a regular arrangement, and they are surrounded by a sea of delocalized electrons, and those electrons are normally moving very freely within the metal. However, when a power source is applied to this metal, the electrons begin to flow in one direction. So when we plug this in, or we turn on the power supply, the electrons will start to flow, and all the electrons will try to move this way. All right, and this movement of electrons is what facilitates the conduction of electricity. For electrolytic conduction now, we have our electrolyte, which is the liquid that we are testing. All right, now ionic substances have anions and cations, which are also called charged ions. So as you see here, your sodium is a cation, or a positively charged cation. Chlorine is negatively charged, right? Now when it's in its solid state, so think of solid salt, we have that rigid lattice structure, and it is keeping the ions held together, right? And it cannot move. But when it is molten or in the aqueous state, such as this, they are free to move, right? Because remember, liquids flow, and the atoms and whatever charged particles are able to move inside the liquid or solution, right? Again, when the power source is applied, the ions move from one direction to another. And the movement of ions, in this case, is called electricity, right? So for metallic conduction, free or mobile electrons are responsible for conduction. However, for electrolytic conduction, our mobile ions are responsible for conduction. Your electrolytes are the liquids or aqueous solution that conduct electricity by the movement of ions. And that is what is inside of the beaker, right? Your electrolytes can be either strong electrolytes or weak electrolytes. All right, so strong electrolytes are completely ionized, whereas weak electrolytes are only partially ionized in solution. So let's take a look at this experiment. So we have our bulb. Right, so this metal is conducting electricity, and it's allowing the bulb to light. Right? We have different substances being tested: aluminum, water, glucose, sodium chloride, silicon dioxide. Right? And as you see here, aluminum, which is the metal, right, it conducts electricity, and our bulb lights. Water does not conduct electricity, neither does solid glucose, solid sodium chloride, or solid sodium silicon dioxide, right? So only when it can conduct electricity, then the bulb will light. Now let's say we add some water to these beakers. Give it a little stir, and we're going to test it again. Silicon dioxide doesn't even dissolve. Right, so let's look at what's going to happen here. Right, so remember, this is glucose. This is an ionic compound, sodium chloride. This is a covalent compound, and our aluminum is in water. It didn't even dissolve. So let's take a look at what happens with the bulbs. Right, see? So with your sodium chloride, it now becomes a conductor. So your sodium chloride is a very strong electrolyte and it allows the bulb to light. Now that you know what an electrolyte is, an electrolyte can be strong, weak, or non-electrolyte. So sodium chloride, as we were looking at before, is a strong electrolyte, right? Because they are able to ionize completely. And the more it ionizes, because it ionizes completely, that means it has more ions in solution. The more ions in solution, the greater the flow of charge. And once your charge flow is great, your bulb will light brightly. However, there are also weak electrolytes. Okay? Weak electrolytes, such as weak acids and weak bases, they only ionize partially, right? Which means we have less ions in solution. Less ions means less charge flowing. Less charge flowing means our bulb lights very dimly. If we have covalent compounds, such as the sugar solution we saw, right? Our sugar solution is covalent, ethanol is covalent. These do not have mobile ions in solution. Therefore, it will not be able to carry a charge and therefore it will not conduct electricity, so your bulb will not light. Now that we understand the flow of electricity, we can now look at the term electrolysis. So electrolysis, if you look at it, it has two words in it, right? One half of the word says electro and the other half says lysis. Electro means electricity. Lysis is actually Latin for splitting, right? So you can use electricity to split certain compounds. So electrolysis is the chemical decomposition produced by passing an electric current through a liquid or solution containing ions discharged at electrodes. What does that mean? It means, let's say we have an ionic compound such as lead bromide. You know, lead bromide is a compound and it has lead ions and bromide ions, right? So it consists of two different types of atoms. So electrolysis is the chemical process which we can use to decompose this compound into the substituent elements. So when we run a current through lead bromide liquid or molten lead bromide, we can actually get pure lead and pure bromine. Let's take a look at this entire electrolytic cell. So again, this is how we draw our electrolytic cell. We have our power source, our connecting wires, our different components such as the switch, the bulb, and these are our electrodes. Now, our electrodes are actually charged, right? So the cathode, because we have electrons flowing from the negative terminal, the electrons build up here and it makes this electrode negatively charged. Negatively charged electrodes will attract positive ions. So all the positive ions will move towards the negatively charged electrodes. Cations move to cathode. This is why we call this electrode cathode, because cations move to the cathode. Similarly, we have our positive electrode. Positive electrodes attract anions, right? So you see all these anions are being attracted to the anode, right? Now the anode is positively charged, right? So anions attracted to anode. And that's a good way to remember it. A lot of students tend to get mixed up. They think anode is negative, but no, anode is positive because it attracts anions, okay? Right, so At the cathode, we have these cations being attracted, and what happens to these cations is that they gain these electrons at this electrode and they become neutral atoms. When it becomes neutral, then we say it has been discharged, right? If we have our anions being attracted to the anode, here what happens, remember the anions have negative charge and they want to get rid of that negative charge. So to get rid of the negative charge, they need to give up their electrons. When they give up their electrons, it's taken up by the cathode, right? So when it gives up the electrons, they become neutral atoms and these become discharged at the anode, right? Now, if you remember from our last topic, do you remember oxidation is loss of electrons, reduction is gain of electrons. So at the anode, we have our loss of electrons from the electrolyte. So at the anode, we have oxidation taking place. At the cathode, we have reduction taking place. Now, the first type of electrolysis we looked at earlier was electrolysis of molten lead bromide. So the only ions that can be present in molten lead bromide, they're going to be molten lead, 2+ ions, and remember it's molten, so it's going to be in the liquid state, and we'll have bromide ions. Again, it's molten, so it should be in the liquid state. We can also have salts such as molten sodium chloride. What are the ions in molten sodium chloride? It's easy. It's just sodium and chloride. Okay, very simple. With dilute sulfuric acid, however, this has more than two anions and cations in it, right? So our sulfuric acid, our acid dissociates into H+ and sulfate, and it's also dissolved in water because it's in the aqueous state. So we also have water in the solution. So we have H+ from the water and the OH- or the hydroxide ions from the water. So dilute sulfuric acid as an electrolyte, it's going to have H+ ions, and it also has two different types of anions. It has hydroxide and it has sulfate. For concentrated hydrochloric acid, right, this means we have a lot of acid and we have less water because it's concentrated, right? So we'll have H+ and Cl ions from the acid, and we'll also have H+ and OH- from the water, and this is the water that the acid is dissolved in. Again, we only have a little bit of water because it is concentrated. You have more H and Cl- ions. Let's look at a few more electrolytes. Dilute sodium chloride now. So that tells us that we have sodium chloride. If it's dilute, that means it's dissolved in water, right? And it's dilute, so it has a lot of water. So our sodium chloride will have these ions, sodium chloride, and water, again, H+ and OH-. Because it's dilute, we have a lot of water, so we have more of these ions in solution. Concentrated sodium chloride have the same ions as dilute, but the amount is different, right? Because it's concentrated, we have more sodium and chloride and less water. Aqueous copper sulfate. The copper sulfate will give us copper ions and sulfate ions. And the aqueous part means it's dissolved in water. Again, it's going to have H+ and OH-. When we have more than one type of cation or anion in our electrolyte, it sort of fights, right, to be discharged at the electrodes. and there are certain factors which affect how they are discharged or how it affects the products of electrolysis. So the factors which influence the products of electrolysis would definitely be the type of electrolyte, the type of electrode used, the concentration of the solution, and the position of the ions in the electrochemical series. And this series is a listing which places ions in order of ease of electrical discharge. And this is something we will be looking at in our next class. All right, so if you have any questions, please feel free to send me a message. Please make sure you take down all of these as notes for your class today. And I hope you liked my video. I hope you enjoyed it. All right, and don't forget to like and subscribe. Okay, that's it for today. Bye.